So we'll study about the introduction, the properties, the terminologies related to the Fibonacci heap, the comparison with the binomial heap, the operations involved in it, and the advantage of the Fibonacci heap. So let's get started with the introduction of the Fibonacci heap. So what is a Fibonacci heap? A Fibonacci heap is a data structure which is used for implementing priority queue. They are not constrained to be a binomial heap because they have different properties from the binomial heap. And in terms of the time complexity, they beat both the binary heap as well as the binomial heap. And that's a great advantage of using Fibonacci heap. Why is it called a Fibonacci heap? It is called a Fibonacci heap because the Fibonacci numbers are used in the running time analysis of the Fibonacci heap operations. Also, every node in Fibonacci heap has degree at most big of log of n, and it has been proved. And the size of a subtree rooted in a node of degree k is at least f of k plus 2, where f of k is the kth Fibonacci number. Now let's talk about the properties of Fibonacci number, Fibonacci heap. So there can be many trees with the same degree, unlike the binomial heap in which only one tree can have the one degree type and the other cannot have the same degree. And it is not necessary in the Fibonacci heap that every tree has exactly 2 raised to k nodes, and the trees are rooted but unordered. That is, a root list is kept which maintains the pointer of every root of every tree, but they are not arranged in the values of their increasing or decreasing values. And the root and siblings are kept in a circular doubly linked list which allow us constant time deletion, insertion and concatenation. Each node has stored the degree, that is the number of childs it possesses. Every node is either marked or unmarked, and this property of marked or unmarked will help us in performing the decrease key operation, which we will see in the future. The minimum edge keeps pointer to the minimum root of the heap. A node will be marked x if it has lost a child since the last time that x was made a child of another node, and a newly created node is by default unmarked, and whenever a node x becomes child of another node, it becomes unmarked. Now let's talk about the terminologies related to Fibonacci heap so that we will easily identify the operations and we can easily understand it. So minimum of h keeps the pointer to the minimum key of the entire heap. N of h equals the number of nodes in the heap. T of h equals number of rooted nodes in the heap. M of h equals the number of marked nodes in the heap. And potential function of the heap equals the number of rooted nodes plus twice the number of marked nodes. Now let's compare it with binomial heap and understand why is it better. So except for create new heap, extract minimum and delete node, all the other 4 operations, that is inserting a node, finding minimum, union of 2 heaps and decreasing key, all these 4 operations are giving big O of 1 in Fibonacci heap, whereas they give big O of log of n in binomial heap. They give big O of 1 when we compare it in the terms of amortized cost. So now we will understand what is amortized cost. Amortized cost is the average cost or the cost that our algorithm performs in the longer run. So for example, if our algorithm performs 100 operations, out of 1000 times it performs one time 100 operations, and for the rest 999 times it performs one operation. So if we take the average, then the average would be turning out that it would take only 1 or 1.5 operations, not near 100. So if we consider the amortized cost in the Fibonacci heap, then we'll get very better results. Now let's get started with the operations involved in the Fibonacci heap. What is create heap? Create heap is basically the creation of an empty heap when we simply initialize number of nodes equals 0, the number of rooted nodes equals 0, the number of marked node equals 0, and the potential of the heap equals 0, and we point the minimum pointer to null. We simply create a heap. The actual as well as the amortized cost is same. Why is it same? Because there is no other terms involved, whereas some in the other operations we'll see that some other operations are also involved which increase the average cost. So the amortized as well as actual cost is same here. Now let's check about insert node. So the insert node has a fixed algorithm in Fibonacci heap. We create a singleton tree and insert it to the left of the minimum number and check and update minimum if the new node is less than the minimum. So we'll check how the insert node operation works. Here we have a Fibonacci heap and we want to insert 21. So we'll insert it besides 3 or that is on the left of 3. So 21's right will be pointing to 3. 3's left will be pointing to 21. 21's left will be pointing to 7. And 7's right will be pointing to 21. So this is how an insertion operation works. So here also the actual cost is big of 1 as well as the amortized cost is also big of 1. Finding the minimum. So simply returning the pointer to the minimum node in the root list gives us the minimum heap element. So there is no complexity like involved. We just return the pointer. So the actual cost as well as the amortized cost is also big of 1. Now the third operation is uniting of two heaps. How do we unite two heaps? Simply connect the pointer of the root of both the heaps and connect the root list of both the heaps. Check which is minimum of the first heap or the minimum of the second heap. Out of them take the minimum and make it the minimum of the new heap, and we can definitely destroy the old heaps. Now let's see how this operation works. We want to unite two heaps. So here are the two heaps. 17 has the minimum pointer of the first heap and 3 has the minimum pointer of second heap. So we'll unite it in this way. 17's right would be pointing to 3. 3's right would be pointing to 21. 21's right would be pointing to 7. 7's right would be pointing to 23. 23's right would be pointing to 24. And 24 rights would be pointing to 17. So we have maintained a circular doubly linked list, and this is how we perform the union of two operations of two heaps in a Fibonacci heap. And so we'll look at the cost. Actual cost is also big of 1 as well as the amortized cost is also big of 1. Now let's check about the extracting minimum. What is extracting minimum? Extracting minimum means the pointer at which we have kept the minimum pointer, we need to delete it and we maintain the other things as well, and so the properties of the Fibonacci heap should also be maintained. How do we do that? So we'll look at it. The first step is copy all the child of the minimum pointer to the root list and then give minimum to the minimum h right, and then for each node of the root list we need to call the consolidate method. So we also need to check what is consolidate method. Let's see it. Here we want to delete 3. Okay, so the first step involved is we need to put 18, 52 and 41 in the root list. So here is the first step. After that we give minimum to minimums right. So 7 would be pointing to minimum. After that we need to check, we need to first create an array of a size of maximum degree, and if in a Fibonacci heap the maximum degree can be of big of log of n. So we'll create an array and the pointer would be pointing to the degree with that child. Okay, so if 7 has 1 degree and the pointer at 1 is empty, then we'll give the pointer at 1 to 7. After that we need to move to right and check again. So 24 has degree 2 and 2 is empty, so we'll give it to 24. After that 23 has degree 0. 0 is not occupied, so we'll give 23 to 0. After that we go to 17. 17 has 0 but 0 was occupied, so we need to consolidate both of them. We need to check who is minimum. The minimum should be kept on the root list and the other one should be made its child. So here it is, 23 is made its child. The degree of both of them was 0. So the degree of both of them was 0. So 0 is freed and they have degree 1. So again we need to check if 1 is occupied or not. 1 is occupied, so we'll do the same procedure. So 7 will go above, 17 will go down, and the degree of 1 is freed. So the degree is finally 2. It needs to check for degree 2. So here both of them had degree 2. So 7 will have its child again as 24 and we'll merge them and the degree will be 3 and 2 will be freed. After that we will go to the 18. 18 has degree 1. 1 was freed, so we'll give it to 18. After that 52 has degree 0. So we'll give it to 52. After that 41 has degree 1 but 1 was occupied, so we need to consolidate. Here it is 18 and 41. So here after that 18 will have degree 2, 1 will be freed, and this is how we perform that delete mean operation. So actual cost is equal to total number of h plus d of n. So amortized cost turns out to be big of log of n. The next operation is decreasing a key in the Fibonacci heap. So what is decreasing a key? Basically decreasing a key means decreasing the value of some node to some smaller value than it. So we'll see how it works. Okay, there are basically 3 steps involved in decreasing key. The first step is the main step and the other 2 are part of it, that is cut and cascading cut. We'll see each of them. There are 3 parameters: the heap name, the node and the new value. If the new value is greater than the old value, then we should give an error that new key is greater than current key. So it does not make sense. You are rather increasing the key. But if not, then we'll assign key of x as k and y as the parent of x. And then we'll check for if y is not equals to null and key of x is less than key of y, then we need to cut h of x, x, y, and then cascading cut h, y. The cut and cascading cut are always performed together. And after that we'll simply point the minimum pointer so that the minimum pointer can be written in big of 1. What is cut and what is cascading cut? Cut simply means remove x from the child list of y, decrementing the degree of y and adding x to the root list of x. Where will we add it? We add it to the minimums left, and then pointer of parent of the x would be null and mark x equals false. Here comes the mark and unmark. And cascading cut, z will give will to parent of y, and if z not equals null, then we'll check if mark y equals false, then mark y equals true. But if that was not the case, then we need to again perform cut and cascading cut, and so this will go on further. But finally it turns out that a decreasing key has actual cost big O of d plus 1 and amortized cost also of big O of d plus 1 plus 4 minus d. But and finally we compare the decreasing key operation, it turns out to be of big O of 1. The next operation and the last operation is deleting a key. What is deleting a key? Basically we have a node and we want to delete it from the Fibonacci heap, whereas we assured that the other properties of the Fibonacci heap are maintained. So we perform two operations. The first operation is decrease key of the given node to minus infinity, and then we extract the minimum operation. Then so the cost is actually also, it turns out big O of d plus 1, whereas amortized cost is also big O of d plus 1 plus 4 minus d. So the final cost in the amortized is also log of n, big O of log of n. So what is the main advantage of using Fibonacci heap? Due to Fibonacci heap, the complexity of the algorithms like Dijkstra's algorithm and Prim's algorithm can be reduced from e plus v log v to e log v plus v log v to e plus v log v. So we have a difference of e log v minus e. Thank you.